Hello everybody, I will start my today's coding practice. So today's question is for the squares, and this is a second video on this question. So yesterday I solved this question with HashMap as the optimization. However, instead of using the HashMap for optimization, I will use suffix tree, which is also named Trie. And the reason why I take this video and implement it again with suffix tree is just for my practice purposes. Yeah, under the constraints of this question, HashTable is good enough and easy to implement, also easy to implement. However, just for practice, I will implement this with try today. Okay, so let me quickly wrap up yesterday's solution first. So in this question, I were given the list of words like area, read, wall, ready, ball, and all of them has the same length. And in this question, my task is to choose 4 words from them, allowing the duplicate. This time, in this example 1, the number of words I will pick is 4 because the characters, the length of each word is 4. So I will pick 4 numbers and I will sort them like this. And and I will try to create the kind of word square with that. So in this question, the definition of word square is that here, if the case row and column reads the same string where 0k, so the first row is ball and the first column is also ball in this example, and the second row area, second column area, third row read, third column read, fourth row ready, and fourth column ready. So all the row and same as the same index are the same. And in that case, this square is called, this list of words is called word square. So that's the definition of this question. And yesterday, I used the recursion for this question. So firstly, I will pick any string from the word bank. For example, I would pick the word bank, ball. And when I choose it, ALL in the first column is determined. And with that decision, I will try to choose the second string. And the second string has to start with A as the suffix. So I will choose any string which begins from A, like area or this time only area. And I will choose area. And then the second column is determined with AREA. So it's now determined. And when I choose a third word, third column, third row, LE is also determined, so I will pick any word whose suffix is LE from the word bank. Then it should be read, in this case, only. And with that, the third column is determined with LEA. And for example, if I find that I can't find any word with the suffix, I will backtrack. So I will, cancel the decision and go back. Or when I choose every word, 4 words, and those forms the word square, in that case, it's good. So I will append it to the return array. To the list. Then I will backtrack and look for another possible, word square. So that's the basic algorithm of this question. And to find the word whose suffix is something like AR or LE or some specific string, I use the hash map. So from the word bank, firstly, I built the hash map. whose key is every possible suffix from each of words. Yeah. Then the value should be the original string. In this case, the hash map should include empty string to bool, B to bool, BA to bool, BAL to bool, BALL to bool, and empty string to area, AR, sorry, A to area, AR to area, blah blah blah. So that's a hash map I built in line 65, and which means this submethod. Yeah. However, in this video, I will try to use the suffix tree for that. Okay. So let me just quickly estimate the do the complex analysis for those. No, sorry. Let me do the complex analysis later after the implementation. So let me start with implementation. So in line 62, instead of building the hash map, I will initiate the try. Okay. Then so I will implement this. I will delete this. And with that try, I mean the suffix tree, in line 82, I will find the words which begins with that suffix. So in this question, okay, let me write it first. So this is some new method. First with suffix. Then I will give there is a suffix tree. Oh, sorry, like this. So in this way, I will find the words which begin with this suffix. Yeah. And I will implement the method. And obviously in this method, I will have the access to the suffix tree I initiated in line 63 because this is the instance variable. Okay, so that being said, in this question, I will implement the class try. So in this way, I'm pretty sure that the code will be more readable. So let me implement it. Like this. So in this way, instead of this, in line 70, I will implement it. I mean, initiate try. Then in line 80, line 90, I will do it like self dot suffix 3 dot words with suffix then suffix. I remand it into try. Okay, so my task from now is to implement the try class. Okay, so let me first initiate defines the node class. So it should include the character, and also it should include the children. So this should be the hash map. And also, because in try, I have to make sure if this is the end of the string or not. So with that information, say I have A and also AB, I have no idea if there is a word A which ends with the middle of the I mean middle of the try. So I need it. So these are the information I need in the node. So that being said, I will implement the initialize method first. So in my implementation, I will have this one. So this is a pseudo node, or I should say pseudo root. So this string itself, this node itself doesn't have the character. However, makes the implementation easier. So this pseudo root exists just for that reason. Then I will have the word. So for each word, I will register the word to try. So I created the register method. So I will call this from the initializer. In this way. Okay, so now I will implement the register method. So I will use this current variable as a kind of pointer to the current node. So I will begin the pointer with the root node, pseudo root node. Then for each character, I go down the try. So when I find the word say B, current.children should have the B node. So if it doesn't exist yet, I will create it. Then I will move to that node. Okay. Then one thing I have to make sure is I have to mark the last character node with its end is true. So let me do it in this way. So in this way, if the current index is ranked word -1, which means that the last character in the word, I will, makes the flag is end to true in the current node. So this is how I register the word into this trie. Okay. So now I will implement the words with suffix method. So in this method, I will be given the word, and I will try to find all the words which begins with that given suffix. So let me say, if the suffix tree is like this, so please think that this asterisk suggests that is and is true. So with that assumption, say I'm given the suffix AC. So this is the end of the suffix node. And what I will do is try to find ACEF, ACE, and ACEGH. So I will try to find and return all these strings. So for that, I think I can use the backtracking. So I will I will keep all the characters I've seen so far as, say, just so far list, like ACE, and then I will try to visit F, and now the list is ACEF, and because its end is true, the flag is true, ACEF is one of the string I have to return. And after that, I will backtrack, and I have only ACE. And also ACE is also valid, so ACE should be also added to the return array. And also, and then I will go down to G, ACEG, then ACEGH. Then I found another string, so ACEGH should be added to the return array and write that. So yeah, I can use the backtracking. So let me keep that in my mind and do the implementation. So the current node start with the root, pseudo root, pseudo root. Then the first purpose for me is try to reach this C node, which is the end character of the suffix. And for that, I will do it this way. So I will try to, go down to the suffix end, but if it is impossible, like the suffix is given suffix with is AH, I cannot go down. So in that case, I will already return empty array. Then I will go down, and now I'm at the position where the end of the suffix. And also I have to make sure that those characters are appended to the chess software array. Okay. So after that, I will start the backtracking. So here I will find the inner function, and in that function, I will go down to the suffix tree, and if I find the end of the character, I will append it to the child solver. Then I will return the array. Sorry. So what I should do is, solver should be here. I will initiate return array. Let me say found words. So in this array, new found words are appended, and then I will call this method with the current node. Then I will return found words. But let me just rename this current to root. Yeah. Because I don't want to use the same name for local variable and shared, in the local variable and local variable, because it can lead to the error. So that being said, I will implement find method. So I can say if root node is end of the word. Oh wait, so firstly, in our implementation, root can never be known. I assert it first, and that being said, I will append the word character of the current node. Then, if this root is end, I've found the word. It should be this. Then what I have to do is append this word to the found words, which is a kind of global variable. Global in this word is suffix method. So, and after that, I will continue, because there actually in this question, the ranks of the words is always the same. However, in the case when there are some different ranks of strings, I have to keep going. In this way. And after that, after this iteration is done, wait a minute. So yeah, if root is end, I will do it. And sorry, after that, here I will find the new word. Then I will pop up the word I appended in this method, so that I can rollback the change. Yes. Okay, so in this way, I can implement the child solver. Trie words with suffix method. And one thing I have to make sure is, if the suffix is an empty array, I need to return any string in the word bank, because in our use case, suffix should be empty for the choice of the first word. So in that case, every word is possible to be chosen and put. So I have to make sure of that. So if the suffix is an empty string, there's no iteration in line 86. So I will immediately go into this find method with sudo node, sudo root. Then in line 94, oh wait a minute, what I'm doing? That's yeah, I will append the character of the pseudo root to chat solver, and I will join it to create the word. So in a case, I initiated the pseudo root with empty string, which is good because here in line 96, empty string is joined with empty string, and word would be end. Wait a minute, what I'm saying? Sorry, the chat solver, which is no, so actually this can be any string. Maybe none is okay. So because I will put the child solver every suffix, and if the suffix is empty, child solver is still empty, and then empty string is joined with and after that every word character, like say abd, is appended. Then all of them would be joined together into the word and appended to the found words list. So in this way, every word, original words in the word bank, should be appended to the found words. So it's good. Okay. So today, let me skip the walkthrough and submit my code. Oh, sorry. Find is just a local function. So root can be none. In which case root can be none. Wait a minute. So in my try, if the key exists in the children hash map, the value should be always the node, not none. But seems like root is now none. So let me find it out. Seems like this is the case when the first recursive function call is done. So self.root should be not none. I will print out current node. Yes, so even here, Sorry. This should be root is not known. And this should be local function. Okay, so the problem here is that, yeah, obviously I should start with find child. Oh, so seems like if the child software is an empty array, it should be, it causes an error. So let me do it in this way. Just software, or maybe, yeah, okay. Okay, so let me just make this pseudo root with empty string. So in this way, it is guaranteed that, wait, child software, oh sorry, non-type bound, which case, sequence item 0, expected string, sorry, so what does it mean? So none is included in the child software, probably because in line 80, I mean, the pseudo root is non character. Why is it? Char in current. Ah, I see. So I have to move the current node pointer, and then I need to append it, the current character. But still the same. Oh, and sorry, it should. Oh, it doesn't matter, but it should be char. And still, none is in the beginning of the child software. Current is self.root. Current children char is current. So the current pointer should be moved from the root pseudo root. However, current char is still known. So why is it? So let me print it out here. So it should be now empty. And I start from the pseudo root. I see. Then char software pen root of char. I see. So here, the okay, if child software is, I mean, if the suffix given suffix is empty, current node is still at the pseudo root. So I have to, you know, ignore that character. Okay, so in that case, one of the, workaround is pseudo root character to be empty string. So in that way, this none will be empty string, and I can form the string area. So it's good. Okay, so let me start. Let me execute the code. Let me check which words are returned. So if the suffix is A-A-R-E-A is returned. Oh, which isn't correct. Okay, so I see. So after finishing the suffix traversal for the suffix string, it at the A position. And then the next char I have to append to the char software list is the next char. So I have to go down to the child. Then for each child, I will append it to the child software list. Then I go to the, I traverse the child. Yeah. I will call the recursive function with the current child. And I have to make sure that again, root.char of this method is already appended to child software. That's what I have to take care. So with that being said, and here, this if root is end, I will append it to the words found words. This should be in front of this. At the beginning of this recursive function. Good. And I have to roll back this change at this. Okay, so let me run my code again. Okay, now it looks good. So now I will submit this code. Nice, accepted. Okay, so let me do the complexity analysis. So the first three, what I will do is, so where's the main method? This one. So what I did is initiate the try, then I did the backtracking. So to initiate the try, it will take, okay, so firstly I will assume that length of the word is L on average. And also I will also assume that n is the number of words. Yeah, so with that assumption, to build the try, it will take L times n. And After that, I will do the backtracking. So, I'll, I mean, so where am I? So here, find squares. I will choose a choice and then I see. So for each possible suffix, I do the recursion. I choose that word and continue the recursion. So I will assume how many times I visit these find squares. It's okay. So this I can be 0 to L. And I will think of the state where child sulfur. I mean, I will think of the state on the board, which where's the chosen sulfur. Okay, so with that in mind, it should be yeah, n to the power of l. Sorry, so n is the number and l is okay. So I will choose each of the word l times, and there are n words. So the possible choice in total should be n to the power of l. And in each of that function, it takes times at maybe yeah, I do the iteration that way. And aside from that, it doesn't take time anymore. Yeah. So for this iteration, the thing I will do is I will given the suffix and I will try to find every possible word which begins with that suffix. And in the worst case, I'm at the root node. And I will try to find every node. I have to visit every path. And also append that word to the return words list. So it will take n times l in total. Okay. Yeah, that's it. Good. And for space complexity, firstly, I need trie, which would take ln at max. Then also what I need to initiate is shared software array, which could be up to, no, this is in trie, but it's up to L. So it can be included in an ln, which is used for the trie. And also, yeah, in the main method, I need to call the recursion, and the number of recursion should be up to n. So this should be the recursion stack space. And also, I need the word bank, which should be returned. I don't do the detailed analysis on how many, I mean, where the squares can be made at max. Let me assume that I have n to the power of L choices, and for each, the word bank should be n squared lengths. I mean size. So this should be, yeah, actually this is the return, array. So this is the extra space. So if I just forget the extra space, I need to think of the one word square at the time, which are in the self.square. So it should be NL. Yeah. Okay. Which is L times 1 plus n to the power of L. It should be this. And for this, it should be Ln. Okay, let me quickly confirm in the editorial. So actually this, time complexity uses a constraint that each character can be A to C. So comparing with my assumption, n is the number of input words. L is the length of the single word. So let me read the answer. Okay, so seems like in this solution, it uses 26. I mean, okay, so to calculate the number of possible ways to create the word square, I mean, it is needed in order to find the number recursive function is called. It uses the 26. And yeah, because every character at every position, I mean, for each position, the option is up to 26. So 26 times, I mean, 26 to the power of L is the number, yeah, possible, possible number of words squared. That's the idea. But in my case, I used n to the power of L. Yeah, so that's what I did. So this corresponds to 26 to the power of L in the editorial. However, the coefficient is L in my case, but the editorial is N. Why is it? Oh, seems like I see. So in my case, I did N times L, and N can be included in N plus N to the power of L as N to the power of L plus 1. And I omitted L plus 1. So that's it. But in this solution, it assumes that, wait, In the loop around the backtracking function, we need the possibility of having each word as the starting word in the word square. So in the main method, the recursive function, number words with that suffix should be up to n, which makes sense. But I have to think of the cost to do the backtracking. So I'm not pretty sure on that. And for space complexity, seems like this is correct. Good. Okay, so that being said, let me finish my today's coding practice. I will review this time complexity again after this video. If I find something, I will write it in the description of this video. Okay, thank you so much. Bye.